Welcome to the third session of this polynomial series. In this video, we will demonstrate what we have learned from the previous sessions and level up with more challenging examples. Apart from demonstrating how to apply the factor and remainder theorems, we will show you the details of the relations between polynomial zeros and its coefficients through 5 worked examples. Hello, math champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything. Welcome back to the series of polynomial. This is the third session of this polynomial topic. In this session, we will continue focus on factor and remainder theorems. On top of that, we will explore the relations between polynomial zeros and its coefficients, particularly on quadratic, cubic, and quartic polynomials. The first example is a question related to the remainder theorem. It tells us the polynomial px has a remainder of -8 when divided by x plus 1 and has another remainder of 4 when divided by x minus 3. The question here is to find the remainder when the polynomial px divided by a quadratic of x plus 1 multiplies x minus 3. The critical point here is to assume that the remainder r is a linear expression of ax plus b, not just a constant, because when divided by a quadratic, the remainder can be either a linear expression or a constant. If assuming the remainder is a constant, we narrow down the scope of possible outcomes, which may lead to no solution for questions like this. So, after assuming the remainder is a linear expression of ax plus b, we establish the simultaneous equations to solve the values of a and b. To do this, we substitute values of -1 and 3 into the variable of the polynomial and have the simultaneous equations of -8 plus b equals -8. 3a plus b equals 4. Hence, we calculate the values of a and b, so the remainder is 3x minus 5 when the polynomial px is divided by the quadratic of x plus 1 times x minus 3. The example 2 is a similar type of question related to the remainder theorem, but it is a literal one. It asks us to prove that the polynomial px has a remainder of the result of pb minus pa over the result of b minus a multiplies x minus a, or in parentheses plus pa, when divided by the quadratic of x minus a times x minus b. Since the polynomial px is divided by a quadratic, we assume that the remainder is a linear one of the expressions like mx plus c. After substituting values of a and b into the variable of the polynomial px, we have the simultaneous equations of pa equals ma plus c and pb equals mb plus c established. Here we use question 2 minus question 1 to obtain the expression of m, which equals the result of pb minus pa over b minus a. Then we back substitute the expression of m into equation 1 to find the expression of constant c, which equals pa minus the result of pb minus pa over b minus a multiplies a. Hence, we have found the expression of both m and c in terms of pa, pb, a, and b. Therefore, we have proved that r is equal to the result of pb minus pa over b minus a multiplies x minus a, then plus PA when divided by the quadratic of x minus a times x minus b. Example 3 is also a question related to the proof that the remainder of a polynomial px is p prime a multiplies x minus a plus pa when divided by a complete square of x minus a, or in parentheses squared. Since the polynomial px is divided by a quadratic in a complete square form, we need to assume the remainder is linear. In this case, mx plus c. According to the remainder theorem, px can be expressed as qx times x minus a, or in parentheses squared, plus mx plus c. Then we differentiate the polynomial px with respect to x, and thus we have p prime x equals q prime x times x minus a, or in parentheses squared, plus 2qx times x minus a plus m. After substituting a into the variable of both px and p prime x, we have two simultaneous equations established, and that are pa equals ma plus c, p prime a equals m. Hence, we solve the simultaneous equations and find the expression of both m and c in terms of a, pa, and p prime a. Finally, it is proved that the remainder r is equal to p prime a times x minus a plus pa. Example 4 asks to find the value of a given that the polynomial x cubed minus 2x squared plus a can be expressed as x plus 2 times qx plus 3. Here qx is another polynomial. Based on the initial inspection, the number -2 is substituted to the variable of the equation. So the right hand side of the equation is just a 3. Then we can calculate the value of a, which is 19. Now we are going to explore the relations between polynomial zeros and its coefficients, particularly on quadratic, cubic, and quartic polynomials. The first case is the quadratic polynomial. We use the standard form of the quadratic polynomial, which are quite familiar with. We also assume that alpha, beta are the two zeros of this quadratic polynomial. According to the above, the quadratic polynomial ax squared plus bx plus c is equivalent to a times x minus alpha times x minus beta. After expanding the right hand side of the equation and apply the coefficient equating method, we have found that the relations between the zeros and the quadratic polynomial coefficients, such as alpha plus beta equals negative b over a, alpha times beta equals c over a. Now we are going to do with cubic polynomial. A standard form of the cubic polynomial is used, and we assume that alpha, beta, and gamma are the zeros of this cubic polynomial. The standard cubic polynomial is said to be equivalent to the form of a times x minus alpha times x minus beta times x minus gamma. After expanding the right hand side of the expression and combine the like terms, we have the leading coefficient a multiplies an entire square bracket in which we have x cubed minus the sum of alpha and beta and gamma times x squared plus the sum of alpha beta and alpha gamma and beta gamma times x, then minus the product of alpha, beta, and gamma. After applying the coefficient equating method, we find the relations between the cubic polynomial zeros and its coefficients. Hence, the sum of alpha, beta, and gamma equals negative b over a. The sum of alpha, beta, alpha, gamma, and beta, gamma equals c over a. And the product of alpha, beta, and gamma equals negative d over a. The next polynomial we are going to explore is the quadratic polynomial. A standard form of the quadratic polynomial is presented here, and we assume that alpha, beta, gamma, and delta are the zeros of this quadratic polynomial. First, we take the leading coefficient a out of the parentheses so that the polynomial inside the parentheses is a monic polynomial. Since all the zeros of this polynomial are given, so the standard quadratic polynomial is said to be equivalent to the leading coefficient a times the product of x minus alpha and x minus beta and x minus gamma and x minus delta. After applying the coefficient equating method, we find that the sum of alpha, beta, gamma, and delta equals negative b over a. The sum of alpha, beta, alpha, gamma, alpha, delta, beta, gamma, beta, delta, and gamma, delta equals c over a. The sum of alpha, beta, gamma, alpha, beta, delta, alpha, gamma, delta, and the beta, gamma, delta equals negative d over a. Finally, the product of alpha, beta, gamma, and delta equals e over a. Example 4 is the question we will apply the relations between the polynomial coefficients and its zeros. The cubic polynomial has zeros of alpha, beta, and gamma. The linear coefficient of the polynomial is an unknown constant k. It asks us to find the sum of alpha, beta, and gamma, the product of alpha, beta, and gamma. Finally, it asks us to find the roots and the value of the constant k, given that the two of the zeros are equal in magnitude but opposite in sign. Since alpha, beta, and gamma are zeros of this cubic polynomial, the product of x minus alpha, x minus beta, and x minus gamma is said to be equivalent to the cubic polynomial px. After the left-hand side of the equation being expanded, the coefficients equating method is applied. Hence, we find the sum of alpha, beta, and gamma equals 2, and the product of alpha, beta, and gamma equals negative 24. Alternatively, we can directly apply the formula established earlier to obtain the results for question 1 and 2. As for question 3 of example 4, we start by assuming the root alpha equals negative beta, and then replace beta as negative alpha in the equation of the sum of alpha, beta, and gamma equals 2. Hence, we obtain that gamma is equal to 2. The next step is to substitute the gamma value, which is calculated as 2, and replace beta as negative alpha. Then we have the equation of alpha squared equals 12. Hence, we have two pairs of solutions for both alpha and beta. Since we have worked out the value of alpha, beta, and gamma, we may equate the linear coefficient of both sides of the polynomial equation to calculate the value k, which is equal to the sum of alpha, beta, beta, gamma, and gamma, alpha. That can be simplified as negative alpha squared. Finally, the value of k is calculated, which equals negative 12. Example 5 is a monic cubic polynomial equation of x cubed plus px plus q, and it has alpha, beta, and gamma 3 roots. There are 4 questions follow. The first one is to find the value of the product of alpha minus 1, beta minus 1, and gamma minus 1. The second question is to evaluate the sum of reciprocal of each root, alpha, beta, and gamma. The third question is to calculate the value of the sum of alpha squared, beta squared, and gamma squared. The last question is to find the value of the sum of alpha cubed, beta cubed, and gamma cubed. Here we continue with example 5. According to the relations of a cubic polynomial roots and its coefficients, we have three simultaneous equations established. The sum of alpha, beta, and gamma equals 0. The sum of alpha, beta, alpha, gamma, and beta, gamma equals p. The product of alpha, beta, and gamma equals negative q. As for the first question, we expand the product of alpha minus 1, beta minus 1, and gamma minus 1. And it equals the product of alpha, beta, and gamma minus the sum of alpha, beta, alpha, gamma, and beta, gamma, then minus 1. So after substituting the values of the simultaneous equations, we obtain the value which is negative q minus p minus 1. We evaluate the sum of the reciprocals in the second question by combining three fractions into one fraction. So it is equal to the sum of beta gamma, alpha gamma, and alpha beta divided by the product of alpha, beta, and gamma. According to the relations shown in the simultaneous equations, the sum of the reciprocals of the roots equals negative p over q. As for question 3, we transform the sum of alpha squared, beta squared, and gamma squared equals the squared sum of alpha, beta, and gamma minus 2 times the sum of alpha, beta, alpha gamma, and beta gamma, which equals negative 2p. As for the last question, we transform the sum of alpha cubed, beta cubed, and gamma cubed into the sum of alpha, beta, and gamma, all in parentheses cubed, minus 3 alpha squared times beta plus gamma, all in parentheses, minus 3 beta squared times alpha plus gamma, all in parentheses, minus 3 gamma squared times alpha plus beta, all in parentheses, minus 6 alpha, beta, and gamma. After collecting the like terms and simplifying the expression using relations in the simultaneous equations, we have worked out the values of the sum of alpha cubed, beta cubed, and gamma cubed, which equals negative 3q. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.